bring your rear cameras for egocentric 3D human pose estimation. In recent years, substantial advancements have been achieved in the development of head-mounted devices for virtual reality and augmented reality applications. Existing HMD designs are generally equipped with camera sensors mounted on the frontal plane of the device. This design choice is driven by several factors, particularly the specific tasks for which HMDs are primarily optimized. For instance, front cameras are the most practical and only option for hand tracking. However, it remains unclear if this camera placement is the best choice for all tasks, such as 3D full-body tracking. Meanwhile, egocentric 3D human pose estimation from body-facing cameras has demonstrated notable improvements over the last few years. However, even the current state-of-the-art method often fails to estimate accurate 3D poses in specific scenarios, such as when head-mounted device users tilt their heads upward, a common movement in natural human activities. This limitation arises due to the conventional designs of head-mounted devices, where cameras are predominantly positioned in the frontal plane, thereby restricting full body capture from egocentric views in many challenging poses. One solution to this challenge involves incorporating additional body-mounted sensors, such as IMU, attached to the user's limbs independently of the head-mounted device. Its drawback is the requirement of additional sensor fusion and reliable communication between the head-mounted device and external devices. Another promising approach is to integrate cameras in non-traditional locations on the head-mounted device. In particular, rear cameras, which are often neglected in existing head-mounted device designs, could provide valuable cues to enhance 3D pose estimation. One of the challenges of working with egocentric rear cameras is that they encounter severe self-occlusions more often than frontal ones. Hence, simple combinations of frontal and rear views as inputs are not optimal for existing egocentric methods, primarily due to their dependence on individual 2D joint detectors without effectively utilizing the multi-view context. Our work addresses these challenges with three key technical contributions. This is the first approach to investigate egocentric rear cameras, inspiring new HMD designs specifically tailored for full-body tracking. Secondly, we propose a new transformer-based module that refines 2D joint heatmap estimation with multi-view context and uncertainty-aware masking, which in turn boosts the accuracy of the estimated 3D human poses with existing 2D to 3D lifting modules. Additionally, we introduce two new large-scale datasets, synthetic data with diverse human motions, and real-world data developed with our new head-mounted device. Our prototypical head-mounted device consists of a helmet and 4 downward-facing fisheye cameras, 2 on the front and 2 on the back. With this device, we create the Ego4View-RW dataset using a multi-view 3D human motion capture studio. Based on the concept of our new head-mounted device, we also render a large-scale synthetic dataset, Ego4View-Syn. The proposed datasets feature not only simple tight clothes typically seen in existing datasets, but also loose ones, such as long skirts and yukata, with realistic cloth deformation that bring additional and new challenges in the egocentric task. See our main paper for a detailed comparison of existing datasets. The proposed method is designed to leverage the multi-view context of egocentric inputs to refine 2D joint heat map estimation, thereby improving the accuracy of estimated 3D poses. We are given 4 view inputs, and we first use a 2D joint estimator to estimate 2D joint heat maps. We also extract 2D joint positions from the heat maps as anchors on the corresponding heat map feature. Next, our refinement module refines the heat map estimation for each view. Here we show an example process to refine the heat map for the front left view. The features around the anchors interact with view-specific joint queries via attention mechanisms to generate multi-view-aware offset features. The offset features are then added to initial heat map features to obtain refined features and heat maps. Here, to better propagate the initial heat map estimation state, we enhance the joint queries with embeddings of the initial heat map and the RGB input. Furthermore, we utilize heat map uncertainty to explicitly guide the refinement module to prioritize the heatmap features with higher confidence. We iterate this refinement process for all views, and resulting refined features and heat maps can be used with existing 2D to 3D lifting modules to estimate a 3D pose. See our main paper for the details of each step. Here, we report quantitative results on Ego4View-Syn and Ego4View-RW. We observe that incorporating additional rear cameras consistently enhances the accuracy of 3D pose estimation, even with more severe self-occlusions compared to the frontal views. Also, our approach outperforms existing methods by a significant margin across all metrics. See main paper for detailed discussions. We next visualize the results on Ego4View-Syn. Compared to existing methods, our approach consistently estimates more accurate 3D poses. It is worth noting that in some scenarios, EgoPoseFormer with 4 view inputs generates lower quality visual outputs than their 2-view version. This underscores our observation that naively integrating front and back views, even with the state-of-the-art multi-view approach, is not optimal. The proposed method, in contrast, successfully addresses these limitations, delivering superior visual outputs compared to the existing method. We also show the results on Ego4View-RW. Overall, our approach yields better visual outputs than the comparison methods. See main paper for more detailed discussions. We animate a virtual human character, using the 3D poses estimated by our method. We hope that the proposed approach, combined with our new egocentric setup, opens new possibilities for many future applications, including virtual human animation, as well as the development of head-mounted devices with novel, non-traditional designs. Thank you for watching our video. Our source code, trained models, Ego4View-Syn and Ego4View-RW will be made available to foster the area of egocentric 3D vision.